So I'll remind you that you need to be pausing the video and trying the questions on your own. You'll get way more out of it if you try the questions first and then listen to my talking. Okay, this question is about halogens. The table lists some halogens and their properties. Complete the table by giving the missing information. So we've got the information they're asking about is the state, so solid, liquid, or gas, and the color. So fluorine is a gas at 25 degrees. So you'll see there's a trend. As you go down, they get more towards solid. So it goes obviously gas, liquid, solid. Bromine is a liquid. And the colors, there's also a trend in colors. They get darker as you go down. And again, this is mainly just memory. Fluorine's pale yellow. Chlorine is green or pale green, but green would be accepted. And then we have our marks. Suggest a state of astatine. As I said, there's a trend. It goes gas, gas, liquid, solid. So astatine is below this one, so obviously will be a solid. Okay, give the letter for the piece of apparatus that is a burette. So that's, we've already talked about that. That is a Q. Q is a burette. Q. Name the piece of apparatus labeled R. So we've already said that. That is a volumetric pipette, but they'll accept pipette. Volumetric or glass pipette, but pipette is fine. Okay, this one wants us it says a sample of bromine atoms contains 42% bromine, 79, 58% bromine, 81. Calculate the relative atomic mass. So our command word is calculate relative atomic mass. So we need to think what the equation is related to that. Also, my students, I've told you guys, you will need a highlighter, and you always need to be looking out for it. Whenever it talks about significant figures, you highlight that in a special color, you draw an arrow where your answer is going to be, and it just reminds you to rethink about the significant figures when you come to the final answer. Really, really powerful technique. Highlight it whenever you see significant figures or units, and you'll save loads of marks. Because it's easy, most of you know what sig figures are. Anyway, let's talk through it. So command word calculate relative atomic mass. So let's write the equation. So relative atomic mass, which is given the symbol capital A, lowercase r, is equal to sum of, that means that symbol means sum of isotope mass times percentage. So that's, and then that's divided by the total percentage, which is 100. So let's do that. So we got sum of isotope mass. So the first one is there, 79. So its mass is 79 times by its percentage, 42. So I've just done this one. And then you plus, so sum of means plus. I'll do this one in a different color. And I'm going to take this. So 81 is the mass of bromine 81 times its percentage, 58. And then we'll divide that by 100. Now, of course, because this is an average between 81 and 79, we know that the answer is going to be at the least 79 and the highest 81. I say that because what happens, students often type this into their calculator and they don't include brackets, and therefore they get like a wildly different wrong number. But you know it's going to be between 79 and 81, so if it doesn't come out close to there, obviously you've made a mistake. Now, I don't think I can bring a calculator up on this, but let me pause. Okay, so that came out to 80.16. But then if you remembered, we had this highlighted and an arrow there, so we know to go to 3SF. This is 4SF. This is 4, 1, 2, 3, 4 significant figures. So whenever you give it 3, you have to round. So if this number is 5 or above, it would turn that number, it would round that up. So this is 80.2 to 3SF. So this is quite a mean question. Try it yourself first. We'll have to work out probability of this one here. We're told that a sample of chlorine contains 0.75 moles of chlorine 35. So we have chlorine 35. So 0.75 moles, or 75%. And then this one, chlorine 37. It's not as much as it. There's only 0.25 or 25%. And it shows us how to work out the probability if they're both 37. So you'd go 0.25 times 0.25 gives you this probability. So basically, there are 4 probabilities. They're both 37 37. They're both 35, 35, or one is 35, one is 37, or one is 37, 135. So let's finish the question and calculate the probability for this one here. So you can see that for having one of them, that would be 0.75. And then the other one would be also 0.75. So we just times those two together to get us our probability. So let's do that in the calculator. 0.75 times 0.75 gives us a probability of 0.5625. Okay, so there's our answer, 0.5625. Always make sure you write your answer where they want it. So always have a look where they want your answer. Explain why the probability of a molecule having an MZ of 72 is not 0.1875. Okay, well, so this one's going to require us to do actually a probability tree. So let's go through. We've got two chlorines. So the first one has two probabilities. It could either be 35 or it could be 37. And the probabilities of 35 is 0.75. And the probability of 37 is 0.25. And when you've added your first chlorine, there's another chlorine. And this one has also got, let's get some space, also got two probabilities. You've got, this next one could be again 35, which is 0.75% probability, or it could be 37, 0.25. So you can see we could have this and this. So 135, 137, and we can work out those probabilities. So that's going to be, let's write it up here. So we've got 0.75 times 0.25, 0.75 times 0.25 is 0.1875. So you might be thinking, hang on a minute, but it is. Well, that's just one way to make it. The other way to make it is, that was when the first one was 35 and the second one was 37. What about the first one was 37? So that's that, and then we've got another probability tree. We could have either 35 or 37. So the first one's 37, and then the second one's 35. So we're going to do this again, but this time we're going to do it backwards. We're going to go 0.25 times 0.75. Obviously, that's the same answer. It's also going to equal 0.1875. However, because there were two ways to make this, we're going to add those two probabilities together. So let's add them together. So the probability is actually 0.375, because it's those two. There's two ways for it to form. You also might notice all of these probabilities will add up to 1. So I guess another way of doing it is that you could have gone 1 minus that, and you would have also got 0.375. I think this probability tree is probably the best way to explain it. Yeah, if I was doing this in the real exam, I would literally use a probability tree like this to explain it. So just checking the mark scheme, actually, they used a doesn't explain it as well, but they used the last thing, and so they basically were like, well, if this adds up, I think this was 0.5 something, and if add those two together, they're obviously going to add up to 1, because probabilities must add up to 1. So if you minus those two values, what the value you're left with is not 0.1875, it's 0.375. So that's the explanation of using the mark scheme, but I think using the probability tree is a better way of explaining it. So it's very tempting when you have a long question like this to not try it yourself first. It's very tempting to skip these questions. Don't do that. If you constantly skip these difficult, longer questions, you'll get really bamboozled by them in the real exam. So pause the video, try it yourself, write as much as you can, then listen to my explanation after you've done that. Okay, so we've got a displacement reaction. So we need to write down displacement reactions to find what that is. It says include examples, reactions in your answer. So displacement reactions are one in which a more reactive halogen displaces a less reactive halogen in a salt. And a salt is where you have your metal and your non-metal, and the non-metal is going to be the halide in this instance. Okay, so we've defined that displacement is a reaction that occurs when a more reactive halogen displaces a less reactive halogen. And that would be from in a salt, so from a salt containing its halide. Notice how I use the word halogen displacing halogen. We're comparing like for like, but it's in a salt. Let me show an example, because we need to show an example anyway. So we know that the most reactive halogens are the ones on the top. Hopefully we remember that fluorine's the most reactive one. Let's use chlorine. So chlorine's very reactive. There's chlorine. Let's react it with a salt containing a less reactive halogen, so anything below, so you've got fluorine, most reactive, then chlorine, then bromine, then iodine, and acetylene. So let's use bromine, so plus, we have to have a salt, so this is going to be, let's choose any metal, it really doesn't matter, let's use sodium bromide. Okay, so there's my halide in a salt, so my halogen as a halide in a salt, and because chlorine's more reactive, it's going to displace, it's going to kick the bromine out, and it's going to steal its position, so I'm going to form sodium chloride, and bromine will get displaced. Now bromine, like all the halogens, exists as diatomic molecules, so I put a little 2 there to show that it's existing as pairs, and you'll see the equation doesn't balance now, because I can't form one bromine from two bromines, two bromines from one, so I'll put a 2 there and a 2 there to balance the equation. Okay, so it says explain how displacement reactions. So this is basically, this proves that chlorine's more reactive. So I think we would add at this point that halogens at top of periodic table are more reactive. Okay. So in this case, the chlorine is more reactive, so we'll displace the bromine in sodium bromide, producing sodium chloride and bromine. And we would see a color change here, and this would help us prove this, because chlorine in solution is pretty much colorless. Maybe got a faint green color if there's enough of it. But this and all the salts are colorless. All of these are colorless solutions, but bromine is definitely not colorless. Bromine in solution in water looks yellow, so this would form going from colorless to yellow. Yeah, so this explains the trend. So all of the halogens will be able to displace the halogen below them, and that proves their reactivity. So I've just checked the mark scheme, and I actually lost a mark here because I didn't say, I needed to say that if there was a halogen, like say there was chlorine reacting with sodium fluoride, this would not have a reaction because the fluorine is more reactive. So I would need to say that, how that proves that if the halogen is less reactive than the halogen in the salt, there will be no reaction. Okay, so give the chemical name for rust. So rust, please say, don't just say iron oxide, that generally gets the mark, but say please hydrated, that's a Y, oops. Hydrated iron, and it's not just say the oxidation state, which is free oxide. So hydrated iron free oxide, please write the whole thing. Explain how painting prevents iron from rusting. So the paint provides a barrier and prevents, well, what do we need for rust? Well, we need, what is it going to prevent? Prevents oxygen and water from reacting and rusting, reacting with the iron. I'm going to add in the word provides a barrier, paint. I'm just going to add the word covers. So that might be a keyword. So covers the iron I think actually between us providing a barrier is probably the mark there, and then talking about the what's it preventing, that'll be a second mark here. Okay, steel is made from iron and carbon. Explain how the difference in malleability of pure iron and high carbon steel affects the uses of these materials. So again, pause the video, 6 marker, do it yourself first, write as much as you can, even if it's barely anything, at least spend a few minutes trying. All right, so steel is made from iron and carbon. Explain how the difference in malleability. So this is an alloy. So steel is an alloy of iron. Alloys have some other elements in it, sometimes other metals or non-metals like carbon. And what they do, if you imagine some pure, let's make some pure iron. So here's some pure iron as a solid. All of the particles are the same size. So these are all going to be ions of iron, because they're all metallically bonded. And basically, pure iron is very malleable because they're all the same size. If I provide a little bit of force there, say I hit this with a hammer, all these particles will shift to the right, and it won't affect the bonding, because the bonding in a metal is between these are all positive ions. Let's try and use a purple, it shows up better. So these are all positive ions, and what's holding them together, you'd think they'd all repel each other, right? But in between them you've got all these negative electrons. Let's just use little negative symbols. So there's all these little negative electrons in between the ions, and the negative electrons can move. So if I apply a bit of force and the layer shifts one sort of ion to the right, the negative electrons are still in between all of these ions, so the metallic bonding hasn't really been affected. So therefore it's malleable. You can hit it with a hammer, it retains its shape, it's not brittle, it doesn't snap. But unfortunately, the malleability is a good thing and a bad thing. So it's good if you want something which is easy to shape. So let's think about a use. When would we want something easy to shape? Like maybe a paperclip. Maybe you want the paperclip to be able to be a bit bendy, so you can sort of move it around and adjust it for fitting onto the paper. So you want it to be malleable, so that's a use, an iron paperclip. For the alloy, so then we have our same as before, our iron, it's all in rows, but this time we've got a few carbon atoms. Carbon's quite small actually. So that's purple, that's right, that's carbon. Carbon. And the carbon atoms are going to disrupt this regular arrangement. So now they're not going to be in this regular arrangement like they are before. So if I apply a bit of force, say I apply a bit of force to this line here, the carbon's sort of going to get in the way and prevent this layer from sliding as much. So it won't be able to slide. So keywords you've got to keep using are slide and layer. Use those words in your answer. Layers. So this is going to prevent sliding and hence make it much harder. So this is going to be much harder, less soft, less malleable. And that's great for majority of things. So generally we want to use steel over iron because we don't want things to be too malleable. If something's too malleable, it's just going to change its shape. Whereas if we're building a building using steel girders, we want it to be hard and retain its shape. So did I mention everything in the mark scheme? Yes, we said that steel was an alloy. We said that the malleability for pure iron is going to be greater. Iron can be used in gates, railings, nails, whereas I said I used an example for paper clips. I guess that's a much better example. I should have said wires actually, yeah. I think paper clips would have got the mark, but wires is a great example where you want it to be really malleable. Steel can be used in, I said like building materials, which isn't on there, but that definitely would. But yeah, anything you want hard, like I guess something, knives is quite a good idea, or tools, because you want it to be very hard. But yeah, I think we would have got that mark and that mark. Steel has different sized atoms. We said that, which means the layers cannot slide. We said that. So yeah, that would have been 6. Okay, so zinc reacts with dilute sulfuric acid to produce zinc sulfate. So here's our zinc reacting with sulfuric acid. There's the sulfuric acid. And then we have a mass of 16 grams of zinc, so that's 16G. I like to write stuff underneath, helps me focus. Excess sulfuric acid, so that's excess. And then we've got a command word, calculate, property volume at RTP. RTP means room temperature and pressure of hydrogen. Okay, so we're trying to work out hydrogen. So I always teach my students to put a question mark on the chemical that you're asked in the balanced equation. So we're asked about hydrogen, and I always ask my students to put a tick next to the chemical they tell you information about. So they told us about zinc. And then the simple steps for these types of questions is always basically, the first job is always to work out the moles of the tick, and then you work out the moles of the question mark using the ratio, and then you work out, and then you basically just answer the question. You go back to the command word and find out what property it is. So let's go and do that. Let's do step 1. So we want the moles of the tick, so we want moles of zinc. Now here's something which is really important, which not enough students do. When you're showing your working, it's not good enough just to show the numbers. You must, and I can't stress this enough. I don't understand. I tell students this over and over again, and just students don't do it, even in year 12. You must tell the examiner which chemical you're talking about. It's not okay to just write moles and then be like moles equals 16 over mR of zinc, which is, what even is that? 65. So writing this without qualifying it that you're talking about zinc will not get you the method marks. You're going to lose so many marks if you don't do it. So just do it. Okay, so we've said we've got moles of zinc, so let's do that in the calculator. So 16 over 65 equals 0.2461. This question hasn't asked about sig figs, so I'm just going to use the full number in the calculator to show that. I'm just going to write down at least 4 sig figs and then write ... to show that I'm writing all of the numbers. So there's my moles of zinc. I'm sure I would have got 1 mark for doing that. Okay, next one, step 2. Work out the moles, and again I'm going to say which chemical I'm doing it for, the moles of hydrogen. I'm going to use the ratio. So can you see how the ratio is 1 to 1? So therefore the ratio is going to be, it's going to be equal the moles of zinc. You don't need to show this working. I'm just showing this so that you understand. But you could just write, if you can understand what the moles of hydrogen are, just write it in now. So moles of hydrogen equals moles of zinc, and apply the ratio, which is divide by 1 times by 1. So therefore it's going to be equal to 0.2461. Okay. And then finally answer the question. So step 3. So what was the question? It says calculate volume. So we need an equation with volume in it, and for a gas, and hopefully you remember that volume is equal to moles times 24. And there's a little reminder there. It does say that the mole of volume is 24. So basically, when it says mole of volume, that says that 1 mole equals 24 dm cubed. But we don't have 1 mole. We've got, so let's write that down. So we've got V is equal to N times 24. This is one of the equations you just need to memorize. We've got 0.2461 ... Remember, use the number in your calculator, the full number, times 24. Let's times that by 24. And it comes out to 5.907. And then it comes out, I'm squaring for 6.9, this goes on and on. Now, just write the whole number from the calculator, absolutely fine. But if you do stop writing, make sure to remember to round it correctly. So the next number here is 2. So therefore, say I wanted to write this to 3 significant figures, that would be 5.91. My only little tip for GCSE is never go less than, if the question specifies give your answer to 3SF, then obviously do that. But say the question doesn't mention it, always give your answer to at least 3 significant figures. So don't write this to 5.9. You probably won't lose a mark, but definitely don't go to 6. Just don't put yourself open to losing a mark. Just write it to 3SF if it doesn't mention it, but do round it correctly. So there's 7 turns that into a 1. So 3.91 dm cubed. Okay, a solution of zinc sulfate is electrolyzed to form zinc on the negative electrode. The ionic half equation at the negative electrode is zinc 2 plus 2 electrons makes zinc. Give a reason why this half equation shows reduction. Okay, so can you see how the electrons are on the reactant side? They're being joined on, so this is showing reduction. Reduction is gain of electrons. So I would say electrons joining or being added to, gained, being added to zinc 2 plus, and that's the definition of reduction. Reduction is gain of electrons. Complete the ionic half equation that could occur at the positive electrode. Okay, so basically it's told you that hydroxide ions are breaking into oxygen and water. This is one of these equations where, to be honest, I would just learn it. It's just better just to learn this one because it's a bit of a pain to balance on the fly if you're stressed. But let's go through how to balance it in case you haven't learned it. So can you see how there are, on the left side there's 1 oxygen, on the right side there are 3 oxygens. So we need more oxygens on the right. How many more do we need? Sorry, we need more oxygens on the left. So I could put a 3 there, but then you'll notice the hydrogens don't balance. I've got 3 hydrogens and only I've got 2. So now I need more hydrogens. Well, let's just bit of trial and error. This is 1. Let's go up 1 more. Let's put it as 2. And now the oxygens don't balance. Now I've got 4 oxygens over here. Okay, well I can go up here, put that as a 4. All right, now the oxygens balance and the hydrogens balance. We also have to make the charge balance. Can you see the total charge is 4 minus? You've got 4 of them, so therefore we need 4 electrons, and that's the balanced equation. A sample of the solution surrounding the positive electrode is tested with a universal indicator. Explain the final color. A sample of the solution surrounding the positive electrode is tested with universal indicator. What are we doing? We're doing zinc sulfate. Yeah, well, what's left? Let's work this out. So basically, we had this in solution. So we had our zinc ions, zinc 2 plus. Now remember, this is water. So water splits up into H plus and OH minus, and then the other negative ion is a sulfate ion. We are shown that we are told that zinc is being reduced. So therefore, if zinc is being reduced, the hydrogen is staying in solution. So the zinc is being removed, which means the hydrogen is staying in solution. The hydroxide ions are being removed. We just shown that at the positive electrode. So therefore, what's left? Well, hydrogen ions. And what acidity are hydrogen ions? Well, hydrogen ions are acidic. So therefore, what color will that be for the universal indicator? It will go red, because we have H plus ions left as OH minus ions removed from water. Okay, so steam can be used to manufacture ethanol, given the other reactant needed for this reaction. So we use ethene. This is the hydration. So because it says give, we can write in the formula, or we can just write in ethene, or the formula C2H4. State the pressure and catalyst used for the reaction to manufacture ethanol. Oh God. I think the pressure is 60 to 70 atmospheres. I need to check that. And the catalyst, hydration of ethene, is using a Is that silica or alumina? Hydration of ethene. No, hydration of ethene is a sulfuric acid or a phosphoric acid catalyst. Oops, that's wrong. H3PO4. State the glucose in grapes can be fermented to make alcohol. State the conditions needed to prevent the formation of ethanoic acid. So, yeah, when you ferment it, the glucose turns into ethanol. But then the ethanol can further react and turn into ethanoic acid if there is oxygen present. So therefore, to prevent, we need no oxygen. But it's got like a special word. To be honest, saying no oxygen probably get the mark, or we'll get the mark, but the correct word is anaerobic conditions. Basically, it just means without oxygen, anaerobic. Explain why fermentation needs to happen in a range of 30 to 40. So it's 2 marks, so we need 2 points. So we'll explain why can it not be above 40. So above 40, the enzymes in the yeast, so it's yeast that we use to do this fermentation, above 40, the enzymes will denature. Basically what that means is they start to break down. And once they've denatured and sort of changed shape, you can't use them anymore. So once it's reached above 40 degrees, it's completely useless. The yeast will actually die. But why not below 30? So if it's below 30, it's too slow. So too low a temperature, too slow. Too low, too slow. Reactions happen too slowly at low temperatures. Esters. This is the structural formula of an ester. So students always struggle with reading structural formula. It is a bit confusing. Let's go through it. So we're asked to translate this into displayed formula. So let's go bit by bit. So let's first do this CH3. I think most people could do that. So the CH3 is a carbon, and then hydrogens are like always on the ends. I know in the position they're not in the end, but basically this is what it should look like. Okay. Then let's move on to this carbon. Let's do this one in a different color. Let's do this in purple. So this is in purple. So there's that purple carbon. And then we got 2 oxygens. Now, hopefully you know that an ester has the following functional group. So we know an ester is going to look like this. So this part must be this part. Can you see how one of the carbons here, it's connected to 2 oxygens? So that's the one, and has no hydrogens connected to it. So that must be that one there. So let's do the oxygens in red. So then we're going to have a oxygen there, the double bonded oxygen, that's that one there. And then we're going to have a singly bonded oxygen. And now let's switch over to another color. Let's do this carbon here in green. There's that carbon. You can see it's got 2 hydrogens like that. So that's that one there. And then we'll just do the rest in black because the rest is straightforward. So you've got 1, 2, 3 more. Just make sure this is displayed formula. You must include every single bond and every single atom. So if you're ever asked to define displayed formula, every single bond, every single atom, like that. Deduce the name of the carboxylic acid and the name of the alcohol that react to form this ester. Okay, so there's 2 parts to an ester. You have this part here, which has the singly bonded oxygen. That's the alcohol part. And then you have this part here, which is the carboxylic acid part. So let's do the carboxylic acid part 2. Notice there's 2 carbons. So therefore its name is 2, which is ethan. So if it was just 2 carbons and an alkane, it'd be called ethane, but we drop the E because the suffix starts with, carboxylic acid starts with an OIC, oic acid. So because this is a vowel, we drop the E from ethane. So it becomes ethan, oic, one word, space, acid, ethanoic acid or ethanoic acid. And the alcohol, let's do the alcohol. The alcohol's got 1, 2, 3, 4 carbons. So that's butane. The end of a alcohol is OL, so we drop the E, so it's butane, butane with an E, but we drop the E because this is a vowel, so it becomes butanol, butanol. Now, butanol, there's 2 types of butanol. We can have butan 1O if the OH is on carbon 1, which is in this case, or if the OH was on this one here, we'd call it butan 2O. So we do need to add that number into the answer. Because it's important. So this is butan hyphen 1 hyphen ol. And that's really important because, yeah, we don't want to confuse it with butan 2-ol, which would react and make a different ester. So you do need to name this butan 1-ol. Okay, so these are the structural formulas of two monomers that are used to make a polyester. Give the name of this type of polymerization. So there's two types of polymerization you guys should know. Addition. Addition is when you have alkenes. These are not alkenes, so this must be the other one, which is condensation polymerization. So condensation polymerization is where you have alcohols and esters joining together. We call it condensation polymerization because a water molecule is produced, a little molecule is produced. Draw the structure of the repeat unit of the polyester formed from the two monomers. Okay, so if we go up to our dicarboxylic acid, in the dicarboxylic acid, let's circle the things which are going to leave. So in the carboxylic acid, it's going to be both OH groups are going to leave, and in the alcohol, it's going to be both hydrogens are going to leave. And then we'll draw everything else exactly as it is. So you can see, let's draw this one down here. So minus the thing that's left. So you can see there's that C double bond O. Let's draw everything else exactly as it is. It hasn't asked for displayed formula, so I can use a mixture of displayed and structural like they have there. So you can see I've just drawn that exactly as it is minus the bits that have fallen off. And then we're going to connect up this carbon here, which I'll do in purple, is going to connect up with this oxygen here, I'll do in orange. So there's the purple carbon, let me make that purple. And then there's this oxygen, which is orange, there it is. And then I'll do the rest of the alcohol in red. There, so then it's going to be this part here, so CH2, 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 O, but then we lost the hydrogen. So there we're pretty much done. We're just going to add on trailing bonds. So we're going to add a trailing bond here and a trailing bond there. And that is the repeat unit. There's no need for brackets because this is a repeat unit. If it asks for the polymer structure, we would add brackets and N. No need for that. This is the repeat unit. We are done. Identify the small molecule form when these two molecules form together. So in condensation, I already said, the molecule formed is water, or H2O would also be accepted. Okay, so a student uses this apparatus to investigate the decomposition, breakdown of hydrogen peroxide solution. Okay, so hydrogen peroxide comes in here. This is probably some sort of burette. There's like a tap to turn it on. We've got this manganese oxide down there. That's a catalyst for the reaction. And a gas is going to be produced, oxygen gas. Oxygen gas comes up here and pushes this plunger out. So this would start off at 0 and be pushed out. Give a chemical test for the presence of water. So this is producing water. Chemical test for the presence of water, 2 marks. So first one is use anhydrous copper 2 sulfate. That's one chemical called anhydrous copper 2 sulfate. Its formula is CuSO4. I probably would write all that down there though, like that, rather than the formula. So we add, so make sure you clear your grammar. We're adding anhydrous copper 2 sulfate, which is white. So this is white, so white solid. If water present, it goes blue. And that's the test for water. What's being created is that blue chemical is basically hydrated copper 2 sulfate, which basically has some, oops, that's the wrong place to put them. You go dot X H2O. So it's going to basically, some water molecules are going to be added into the crystal structure, turning it blue. But you don't need to write that. Simply saying the name of the chemical and it goes from white to blue, solid is good enough. Okay, in the first experiment, the student uses hydrogen peroxide solution with a concentration of 0.02 mole. It's quite a low concentration. The graph shows the results. The students do, they plotted what they plotted. They plotted time. Oops. So they've got time versus volume. Okay, and can we see in the graph that it's starting off quite steep. It's getting sort of stopping around here even. In a second experiment, the student uses hydrogen peroxide solution with a 0.025. Can you see that's increased the concentration by about a fourth, or by a fourth. So the concentration's increased. All the other conditions remain the same. So on the grid, draw the curve you'd expect the student to obtain from the second experiment. So if we look back at the reaction, this hydrogen peroxide is the only reactant, turning into water plus half an O2. Oops, let's draw it down there. So plus half an oxygen is forming, half an O2. So if you have more concentration, it means you've got more moles, so you're going to be producing more. How much more? Well, we added about a fourth. We added a fourth more. We added 0.005 more, so we're going to get that much more gas. We produce 40 gas. We're going to get 1/4 more. What's 1/4 of 40? That's 10. So basically, the line's going to stop there. So we're going to produce more. Also, because the concentration is higher, we know from our rates of reaction, we know to increase the rate of reaction, we can increase concentration, temperature, pressure for gases, surface area for solids, catalyst. So this is one of the things that increases the rate of reaction. So an increased rate of reaction rate on a time volume graph, or a time concentration graph, or a time mass change graph. On any of these graphs, the gradient is equal to the rate. So if we're increasing the rate, it means the gradient is going to be steeper. So basically we need to, let's use a different color. It's going to be starting at 0, but it's going to come out steeper. And it's going to end here at 50, because we've got, it's going to be hard for me, this pen sort of sucks. Well, I mean, I suck at using it. But that's meant to be a straight line. Pretend that's a straight line. So basically it's going to stop at 50. And there's my 2 marks. 1 mark for going, higher gradient, another mark for stopping at 50. On the grid, draw the curve you'd expect the student to obtain for the second experiment carried out at a lower temperature. Okay, so we're doing the same experiment again at a lower temperature, so we're going to have a slower rate. So we're still going to end at the same point. We're still going to produce 50 cm cubed of oxygen, just going to take longer. So let's exaggerate it and let's do a really, oh God, let's start that again. So we want to get to the same point as before, but maybe I'll start here. So we want to get to this point, but we're going to go for a lower gradient. Actually, I don't like that at all. Let's try it again. I want to have a curve, because it should be a curve. There we go. Something like that. I still don't like that. The reason I don't like it is because it looks like a straight line. It should be the reaction, even though it's a, let's just start from this side. So I want to go up slower. And it's slowing down, slowing down, slowing down, slowing down, slowing down, slowing down, and it's stopped. That's much better. Although it should be, again, I'm using a pen on an iPad. I sort of suck at drawing it. That should be the way of, it shouldn't be wavy. It should be like this. Oh, I can do it. Just didn't do it very well there. Something like that. Anywho, if you make a mistake in a graph, rub it out. So do your graphs in pencil, rub it out, and redo it. Let's try that again. God, I just can't do it with the computer. All right, anyway, moving on. Okay, so this one we've got potassium iodide has been suggested as an alternative catalyst, and we are asked to describe a method to show how it's an alternative catalyst. So the main concept about this is basically basic experimental procedure. You're changing one thing, so our independent variable is the type of catalyst. So we've already done the experiments with the first catalyst, now we're changing it for this new catalyst. So most of the marks here are going to be just for keeping everything the same. So it's about all the control variables. So basically we're going to run the experiment again, and we're going to keep the same temperature, same volume of H2O2, everything the same. And then we're going to measure, what did we measure last time? We measured volume. So we measured the volume up to 50 cm cubed. So we're going to measure the time it takes to get there. And if it's a better catalyst, it will take less time to get to 50. And if it's a worse catalyst, it will take longer to get to 50. And then we can, once we've done the experiment, we can plot a graph, and we can basically see the one which has a sharper gradient gets there first is the best catalyst, and then the one with the, this will be the worst catalyst. So it does get there, it just takes longer, so it's not speeding up the reaction, because catalysts speed up a reaction. So the catalyst which speeds up the reaction most is the best catalyst. I'll just pop up the mark scheme now. Oh, I forgot to say that. I forgot to say, yeah, so same mass. We must use the same mass of the catalyst. We said same volume, same temperature, time it, record the volume of gas produced in a given time, or record the time. This is probably the better idea. I think it's what I said, to record the time for a certain volume. We said 50. So record the time, plot the graph and compare the gradient or steepness for each catalyst. And we said this one, the most effective catalyst gives the fastest rate, hence the steepest gradient. Okay, the equation shows one possible substitution reaction that occurs during methane and chlorine. So we're seeing this is chloromethane. Chlorine's being, the hydrogen's being kicked off. Can you see all 3 hydrogens are removed and the chlorine's replaced it, substituted it. We've got a bunch of HCl. Complete the reaction profile diagram. Okay, so these ones down on our y-axis, sorry, x-axis, this is progress of reaction, or coordination is the way we call it in IB, progress. And basically, can you see how this says delta H equals negative? Okay, so we've got to work out the bond energy for the CCl bond. We're given delta H, and we know an equation which leaks bonds broken minus bonds formed. So we've got enthalpy change is equal to bonds broken. That's our reactants. You have to break the bonds first in a reaction before new ones are formed, minus bonds formed. And like the standard sort of equation is, we'd be calculating enthalpy change, but we already been given that. We've been given that it's minus 339. So let's put that in. So that's underneath bond enthalpy change. It's minus 339. That's our enthalpy change. Hopefully you can spot the bonds here, which we need to break. Let's draw it out properly, or let's draw it out there. So you can see you've got CH, this is a chloromethane, and it looks like that. So you can see they've got those bonds. Then we've got some Cl-Cl bonds, 3 of those. Okay, so let's put it into the equation. So the bonds we've got to break are 3 times CH bonds, plus, this is sum of, minus sum of, so 3 times CH bonds plus 1 times CCl bond. Sorry, CCl bond, so carbon, chlorine bond, that's that bond there. That's the one we're trying to calculate. Here it is. So that's going to be like our X. So we could say let CCl equal X. We can put X in our equation in a moment. What else do we need to break? We need to break plus 3 times Cl bonds. So that's all our bonds we have to break. And then bonds formed, so it's going to be minus bonds formed. We've got 4 times Cl bonds. So, oops, that's CCl bonds again. That's again, that's X. So we're trying to calculate plus 3 times HCl bonds. So you can see over here we've got those carbon-chlorine bonds, and we got 3 lots of HCl bonds. Okay, so let's put some numbers in. So equals 3 times CH bond, that's 3 times 414 as given here, plus CCl, that's what we're trying to calculate, so plus X, plus 3 times CCl, that's given there, so that's 3 times 242. Oops, that's rubbish too. Let's try that again. Let's put that all in brackets, and then minus the bonds formed. I'm able to move my face up the way. No, just draw myself. All right, let's do that here. Okay, so we've got 4x, because that's what we're trying to calculate. CCl bond, plus 3 times HCl, so that's going to be 3 times 4, 3, 1, close brackets. Okay, so let's solve all that, leaving the x's. So that's going to come out to, what we got to one calculator. 3 times 414. We've got 1242 plus x, 3 times 242, so plus 726, and then we have minus, let's put brackets, 4x plus 3 times 431, so plus 129, and that's all going to equals minus 339. So I'm running out of space, so I'll create a new thing, and then we'll basically put all those and get an x. Let's have a look. Let's pause. Okay, so adding all this stuff up, we're left with this. So we got our minus 339, and then we got our, this is our bonds broken, and this is the ones which are forming. Okay, so because we're minusing 1, this is x from 4x, that gives us 3x, or minus 3x I should say. So we've got minus 3x, and then we will minus, so we've got 1968 minus 1293. So that is positive 675 equals minus 339. Let's throw everything onto the other side. So we've got minus 3x is equal to minus 1014. We know x is going to, well, we can see that x, we want it to be positive, so let's times both sides by minus 1. So we've got 3x equals 1014. And now we'll just divide by 3. So therefore x is 1014 over 3, 338. And that will be in the same units as here, kilojoules per mole.